with Python and Apache Spark, and we can kind of get into what that means in a little bit. But first, let's kind of go through the agenda just so you can know what to expect. I definitely haven't met all of you, so I'm going to give myself a little bit of an introduction. I'm going to talk about what we're going to go over today, what we're going to learn. I'm going to talk about what you might need to know before we talk about word embeddings, right? I know that people come from a lot of different backgrounds in this group, and I think that's really cool, and that's one of my favorite things about it. But with that being said, I'm going to try to level set on some basic machine learning stuff before we jump into word embeddings. And then when we do jump into word embeddings, I'm going to cover 4 main things: what they are, how they're created, why they're useful, and then finally, how we can actually use them, right? And then I'll give you some guidance on what to do next if you find this interesting, no matter where you are in like a machine learning education journey. All right, so who I am. So somebody else said they just moved here pretty recently. I moved here in July. I moved from Cincinnati. I lived in Cincinnati for the previous 7 years. I currently work as a curriculum engineer at Databricks. There I design and develop machine learning educational content, primarily instructor-led courses, online facilitated courses kind of like this. And then I also work in our certification exam space. So I write certifications for data science, machine learning, and data engineering. Previously, I worked at a company called 8451 as a data scientist. That company is a subsidiary of Kroger. I did a lot of recommendation system work there, so machine learning stuff there as well. And when I lived in Cincinnati, I was a Python instructor at the University of Cincinnati. Some non-technical things. This is wrong. It says I like pizza and soccer. That's definitely wrong. I love pizza and I like soccer. I'm developing some strong opinions about what the best pizza is in Southwest Florida. So if anybody wants to talk about that, join the Slack channel. Actually, we could make a pizza Slack channel. You can just Slack me for now in a direct message and we can talk about it. Or maybe it's important enough for general. I also have a puppy named Millie. We got her at the very beginning of January and she's amazing. I love her, but I get a lot less sleep. She's definitely a Florida dog. So you can see a picture of her here at the beach. She used to go to the beach like once a month, and now, well, before we were locked down, we started going like once a week because she just had the time of her life and she would finally sleep through the night. So that's just 2 fun little things about me as well. So you kind of know who's talking here. So with that, let's kind of jump in. Next thing we're going to talk about is what we're going to learn today. I mentioned that I work in education, right? I build curriculum. So all of my talks are always formatted like some type of curriculum. So I try to not be very lectury. Sometimes it happens. One of the things I do try to do though is make sure that all of you know what you're supposed to get out of this, right? So I had outlined some objectives, right, for you. The first thing, it would be great at the end of this if you have a general high-level understanding of machine learning. Like I said, I know everybody comes from a different place. If you can leave with this, that would be excellent. Also, understanding what word embeddings are. That is the point of the talk after all, and why they're important to machine learning, at least conceptually. And then finally, you can at least know what tools to use to go ahead and create word embeddings and have resources to go to get started in that process. So what do you need to know before we do any of that, right? There are a few things. In the title of this talk, right, there was something called Apache Spark, right? Oh, I see there's a lot of people talking about pizza here. This is worth a pause. A lot of Downtown House of Pizza votes. Homemade, totally agree. Dante's is excellent as well. Bellacino's is always good. I have not tried Grandpa's and Bonita. Nice Guys I haven't gotten to yet, but it's next on the list. All right, we'll move on. Apache Spark, right? So Apache Spark, what the heck is it? It's a distributed data engine, right? And what does that mean? So I'm going to be using this throughout the demos today. We'll get into what it means in the next slide, but just some details initially. It's open source, right? It's an open source project. Anybody can use it, can download it. It's general purpose, right? So while it is data specific, it can be used for machine learning, right? There's a SQL engine associated with it. You can do data streaming, you can work with graphs. It works across the board with data. So it's a general purpose. It's general purpose as far as data goes. It has APIs in Python, which is what I will be using today. Scala, Java, R, and as I mentioned, a SQL engine. It was started in 2009 by Matej Zaharia at the University of California, Berkeley. It was came out of a place called AMP Labs, which if you're not familiar with, essentially was like a collection of like the smartest people working on solving big data problems. And Apache Spark was really the big thing that came out of it. The people who created Apache Spark in AMP Labs went on to form Databricks, the company that I work for, as a big data and artificial intelligence company. So that is kind of the story behind Databricks, right? It essentially was born with Apache Spark, and now we do all sorts of big data and artificial intelligence things. For those of you who do work in the data space, we also have created products like MLflow for managing the machine learning lifecycle. Koalas, if any of you have used pandas before, Koalas is pretty similar to pandas, except for it works with Spark. So it's like the pandas API, but it is all Spark under the hood. So it's really slick. It's really cool. So if you work in the data space, I recommend checking that out. That's the end of the Databricks commercial, I promise. We are going to talk about Spark a little bit more here, though, because I skipped over this big thing here, distributed cluster computing framework, and what that is, right? So sometimes data is too big for a single computer, right? This isn't a new concept to a lot of people. You can see here, right? I spent a lot of time making this table bigger than this computer to represent the data is too big for a single computer sometimes. But really that can be because, it doesn't fit on the disk, right? The storage, there's not enough storage on the computer, or maybe it doesn't fit into memory, right? So when data is being transformed or manipulated in memory, copies of that data are created. Things can be cleaned up with garbage collection a lot of the time, but not always. And data can explode. And then when it explodes, it becomes too big for the computer, and the computer slows down, the process slows down, and you're working with data ineffectively. So what do we do about that, right? If that's the case, what can we do? Well, we use a distributed cluster computing framework, right? So if you see over here, we've taken this big table and we've split it into 8 partitions, right? So this is the same data, it's just in a lot smaller pieces. And then we also have 4 smaller computers here, right? A cluster of smaller computers. And we use those smaller computers to do the same data operations we were trying to do over here, but just a little bit at a time, right? So there are a few advantages to this, right? The first one is that now my data fits on my computers, right? I can at least accomplish the task I was setting out to accomplish. A second major advantage is that not only can I accomplish the task, but it's going to happen faster because all of these can be parallelized, right? Over here, I could only do a single task at a time. Now, each of these little computers, right, each of these nodes in this cluster can be computing tasks in itself. And then finally, it's now fault tolerant, right? If things slowed down while using a single computer, the whole process slowed down. If it failed, the whole process failed, and there was no coming back from that. If one of these nodes goes down, right, these other 3 are still running, and this 4th one is actually going to spin itself back up because the entire brain behind the operation is up here at what we call a driver node to the cluster, right? So everything's being controlled from up here, and this is effectively what Apache Spark is, right? This is a simplification, but it distributes a large data set across a variety of worker nodes, or a number of worker nodes, to parallelize execution and to make execution fault tolerant. That's the last of the Spark, but I'm going to be using it, and you're going to see in a few cases where Spark is a lot more effective than just base Python. Also, if anybody has any questions, feel free to drop them in the chat or unmute yourself and ask. I'm definitely not a wait till the end kind of person, so feel free to interrupt me and we can talk about it. All right, so now moving on to the next thing you need to know, which is a little bit of machine learning, right? We're not going to get into any math today, don't worry. We're just going to talk about some concepts. And the first concept a lot of people learn in machine learning is that most machine learning can fit into one of two categories, right? The first of those categories is called supervised machine learning or supervised learning. Supervised learning is when you're learning to predict or estimate some type of target, some type of thing based on input data, right? So if any of you are familiar with the idea of linear regression, linear regression is an example of supervised learning. So what this does is we have a bunch of input data, right? A bunch of metrics, measures, features, a bunch of data that can be used to predict something else. A common example I like to use is whether or not it's going to rain, right? So we can look at the humidity, we can look at the cloud coverage, we can look at the temperature outside, all of this information at like 9 a.m. and we can use that to predict whether or not it's going to rain that day. Well, in order to do that, the computer, the machine, the algorithm needs to be able to learn the relationships between humidity and the rest of those features and whether or not it's going to learn. So what we do is we feed the algorithm real data, actual data. We have all of that humidity information, all of that weather information, and then we also have whether or not it actually learns that day. So this is data that, or whether it actually rains that day. So this is data that was in the past. We apply it to this is what my representation of machine learning, apply it to the algorithm. And on the other side, what comes out is a model, this green line, that can look at all of these different features, right? All of these black little pieces of data, and it can estimate whether or not it's going to rain that day based off of all of that information, right? No one's going to talk to me today because we're all on mute, but I can see some of you. So if we could do like a thumbs up on how people are feeling about some of this. Yeah, good. All right, cool. Thank you. The other, oh, yeah, whoa, yeah. Another concept or the other category is unsupervised machine learning, right? So this is usually not quite as common in practice, at least traditionally, but the concepts are really important. So what this is you're still supplying all of that input data, and but you're not supplying a target, right? Or you're not trying to actually predict anything. So what you're going to do is you might give an algorithm, right? Still daily data, right? The humidity, the temperature, the cloud coverage, things like that. And then what is going to come out, instead of predicting whether or not it's going to rain, it's just going to look at the relationships between all of that information, and it's going to end up categorizing days based off of that. So what you might end up with is like a really cloudy day, right? Or like rainy days. You might end up with sunny days. You might end up with, really hot and humid days. But it's just going to end up, like kind of clustering that information. Again, this is a little bit of a simplification, but that's a general example of unsupervised learning. The important thing to remember is you're looking at relationships between the data. You're not actually trying to predict anything. The nice thing about categorizing machine learning in these ways is that they can then be used to solve real world problems, because a lot of our real world problems fit those two scenarios, right? So an example of predicting book sales based on the book author's previous sales on their previous books, maybe the price of the book that you're trying to set it at, the release date. You can use all of this information from the past and look at how books sold given all of that information to learn the relationship between that information and how well a book actually sells. So if you're looking at trying to release a new book, you can set how much has this author's previous book sold, right? Where do we want to set the price? When do we want to release it? And you'll end up with an estimate for the amount of sales. An unsupervised learning example, right? I threw out the term clustering. We can cluster customers into actionable groups. So say I work at a retailer like Publix, we can cluster customers into groups based on their spend behavior, visit frequency, right? Modality, whether they're shopping online or in person. And then those groups are really actionable because I can say, hey, I know these customers, really like cheap items, but they also, come every single day. Right? And you can work with those customers differently than you had in the past. So that's an example of unsupervised learning. And another example of supervised learning, we could identify what calls are fraudulent, right? When we get calls on our phones and we don't pick up, based on who's making the call, right? The length of the call, whether or not somebody answered, right? That kind of information as well, right? So these are examples of how machine learning can be applied in a real world setting, but they all have something in common. And I'm wondering if anybody has any idea what that is. So we have three different types, or we have three different problems, right? We have two supervised problems, right? The ones, my pointer's gone. The book sales one and the fraudulent calls one. We have an unsupervised learning problem, but they all do have one thing in common. Data. Yes, actually, yes, for sure. They all do have data. And what is that data, right? So all of that data generally follows a certain form or of a certain type.
Is historical data?
Yeah, historical data and historical numeric data, right? So we're learning from the past, right? And all of these things have happened. And they're all being measured, right? And they're all being measured in numbers. But a lot of examples in the real world don't have numeric data, right? And those have been limited in machine learning problems, or those couldn't be solved by machine learning for the longest time, right? Because as an example, right, like what if we want to look at, we're talking about customers, what if we want to look at their comments, right? Or their reviews on products? We have to have somebody go through and read each one of those individually to be able to make sense of it. There's nothing to really measure there. Or maybe, we work for a newspaper outlet and we're trying to recommend articles to certain customers, right? Well, we want to know what that article is actually about, right? You can tag it, but that's a lot of upfront work. So there are a lot of cases in the real world where we don't have that numeric data, like how much a book is sold, to use to solve that problem. And this is effectively the field of natural language processing, right? Text mining might be another term you may have heard, text analysis. And there are a few things you can do in this space, right? The first one we're probably all familiar with is the word cloud, right? This is counting words. It is very simple. We can count words, right? The more times the word occurs, the larger it is, and theoretically those words are important, whatever that means. And then it's commonly visualized in this way. Another example is sentiment analysis, right? So sentiment analysis is a way that we can look at the sentiment associated with words. Some words are positive, other words are negative, some words are neutral. And we can see how positive a collection of words is, like an article, and then assign an overall positivity score to that. And that can be really influential, right? We've talked about customer comments. We can know if a customer is happy or sad a lot of the time based off of this information. And then finally, right, another common example is topic modeling. So topic modeling is a little bit more creative. It's based off of a little bit more complicated math, but what it does is it organizes words or articles or whatever into topics based on which words appear near one another most frequently. So I think this is best explained through an example, right? I brought up like a newspaper outlet, right? So imagine I'm working for a newspaper and we have a finance section and we have a sports section and then we have a local news section, right? If all of the articles in the finance section are talking about, the stock market, are talking about like people filing for unemployment, people talking about anything related to that, right? Those words are going to be kind of associated together in a topic of finance, even if we don't label that article as finance to begin with. Because they appear around each other in the same articles, they're going to fall under that topic. The same idea could apply to sports, right? If you're talking about like, spring training, something like that. With a local news topic, you might see things like beaches, right, being closed, or like a bunch of cars catch on fire at the Southwest Florida airport, right? A lot of that information might be grouped together. And the important thing is that, right, like local, like fire and the beach aren't related at all, but because they're being written in articles close to one another, they're going to end up being in the same topic. So essentially it can tell us what a document is about. So these are three ways that we can kind of do analysis with text, right, with words. But it all is pretty limiting, right? And it's limiting for different reasons. I think why a word cloud is limiting is pretty easy to see, right? It requires a human to interpret it, right? How are you actually going to act on that information? Nobody really cares if the word source code is written a lot of times. Sentiment analysis, right? Maybe a little bit more useful, but it's not really scalable because you need to predetermine how important each word is, right? Before you do that, right? Is the word good better than the word great, or is it worse than the word great, right? And that's hard to tell. And then finally, topic modeling, right? We can assign, words and documents to topics, but again, that's not really actionable, right? We can group them together, but then what do we do with that information? So the reason I'm bringing this up is that I want to make it clear that it's really hard to do machine learning, which is really just math, on text, words, and language, right? All of these things have been built for numbers, for numerical data, like we just talked about. So this is what we have, right, for text, right? And that is nowhere near what we have for numbers. So what do we actually do about that, right? We can try to get really creative, but maybe being really creative is rethinking the situation, right? Maybe instead of finding ways to use text, we find a way to turn that text into numbers, right? This is a different way of thinking about it. I'll admit the first time I heard this, I was like, that sounds like something from, like a movie like How High or something like that. It's like, what if we turn the text into numbers? But as you'll see, right, like, thank you. He unmuted himself to chuckle. But as you'll see, it really is very effective. And this is what word embeddings are, right? Word embeddings are text or words represented as numbers. So I guess I'll stop here real quick before we dive in. Does anybody have any questions right now? People feel like the pace is good. Yeah, cool. All right, I promise we're getting to code soon. So word embeddings are essentially vectors that represent words. And when I say vector, right, I mean vector just like you would find in a programming language, or vector just like you would find in math, right? We have a word. In this case, our word is add, and that word add, right, has this vector with 0.12 as its first element, negative 1.45 as its second element, and so on until its final element is 2.54. And you can see we also have a vector for words subtract, grandmother, grandfather, margarita, pizza, and margarita, right? Now, there are a few things that are important to recognize about these, right? The first one is that every single word only has one vector, right? So the word add has this vector, and that's it, right? In this word embedding model, right? You can't have another way of representing the word add. The next thing to remember is that each word embedding is unique to that word, right? So the word add has its only one vector, but add is also the only word, or that vector is also only associated with the word add. So each one of these is unique. While they're unique, they all have the same number of elements in them, which means that they're in the same dimension space or linear space, right? And I think the easiest way to hammer that home is through a visualization, right? So we all remember plotting points on like an XY chart, right? Scatter plots, things like that, right? We can extend that to be a lot more, to be in a higher dimensional space, right? So this example, we have 3 dimensions, right? We have our x-axis here, we have our y-axis here, and then we have our z-axis going backwards, right? Going in depth, right? So a lot of times word vectors will have 100 dimensions, but they're frequently represented in 3 dimensions visually, for just for clarification. And each one of these points, each one of these words, right, represents a point, just like it would an XY, like an XY point on a scatter plot, right? But we have more dimensions this way. So the word add, right, with its vector that we just went over, each one of those points corresponds to one of these dimensions, and then we're going to be able to plot the word add on that graph. The same thing with subtract, right? The same thing with grandmother and grandfather, Margarita and Margarita, right? So they're all going to be on there in some space, and that's important. And we'll get into why that's important, right? But first, look, I want to talk a little bit about how they're created, because that can help drive the context on why they are all in that space. So the first thing we're going to need to do to create a word embedding, right? To create these numeric representations of words that don't just come out of nowhere, right? We're going to actually need words, right? And these words come from something called a text corpus. So I've thrown around the word document a few times. A text corpus is a collection of text documents in all cases, right? But this can come across in a lot of different ways. So all the way on the left here, right, we have a bunch of different paragraphs of text. Each one of these paragraphs could be a document, and the page that they are on could be a corpus. We could extend that and make the pages themselves the documents and the book the corpus. But frequently, these text corpuses are very large, right? So we're going to have books, right? The whole book is the document, and maybe your home library or your bookshelf is the corpus. So all of our text is organized that way for a lot of natural language processing problems. And that's going to be important. I'm going to use the terms corpus and document throughout the rest of this talk. So that's just kind of to set that stage there. Once we have our text corpus with our documents, right? Our book with our pages, or our bookshelf with our books, we're going to organize it in some way. And the most common way to do this is something called a document term matrix, right? So here is our matrix, right? You can see our rows are our document numbers, right? So you could imagine this would be the book titles of the books on your shelf. And then on the columns are going to be the actual words that are in that matrix, right? Or actual words that are in those books, right? So we've been using the word add, subtract, and grandmother. But as you could imagine, if you had 6, 10, 100, 1,000 books, you would have a lot more words here, right? So this matrix gets very big, very fast. And that's why it's important to use something like Apache Spark to do work like this, because this explodes and then we have to do a bunch of math on it. And a lot of single machines, single computers aren't able to process it very quickly, right? It is definitely a computationally intensive task to even hold this, let alone operate algorithms on top of it.
Hey, Mark.
Yeah.
Is a corpus specific to a model, or could you use like the Library of Congress for all your models?
Good question. So a corpus is a good way of thinking of it is like a corpus is a text data set, right? So it could be used for any model, right? Just like a data set could be used for any model or any problem. So a text corpus is really just, you know, a collection. I mean, it's essentially like a library of books is a good way to think about it. And then you could use it for any model later on. Does that answer it?
Yeah, it sounds like it's very reusable, and
For sure.
you wouldn't have lots of corpuses.
Correct. Yeah, yeah. And we'll get into, you know, kind of why it matters when you might want a different corpus, when you might not, a little bit later on in a demo.
Great, thanks.
Cool. Yep. So we represent our data in this way, right? And then what word embeddings are is essentially mappings, right? Projections. You can call the term whatever you want from that large document term matrix into these word embeddings that we already talked about, right? And the process of getting from here to here is the machine learning. And we're not actually trying to predict anything, right? So this is a form of unsupervised learning as an overall task, right? We're just trying to take data, we're trying to find the relationships between all of these, and then we're trying to represent it in a different way.
Mark, there's a question in the chat for you.
Oh yeah. Generally, you take out super common words like a, the, that, the, that, etc. right? Absolutely. So before you create this text corpus, right, a lot of words might not be very useful, right? Filler words like write, I say write all the time. I would take that out of a collection of text that is me speaking, right? Words like the, that, you're going to remove all of that. And that is that is part of something that we call text pre-processing to these types of problems, right? It's essentially cleaning up the text. You know, you might have misspellings, you might have emojis, you might have all sorts of stuff depending on what your text source is, and you want to clean that up. A really common pre-processing task in kind of the old world of natural language processing, that sentiment analysis stuff I showed you, word clouds, topic modeling, would even be to like lemmatize or stem words, right? So people would remove tenses from words because it was just much easier to understand the word run versus running or ran, or you know, you could come up with a bunch of different examples. So yes, that's all part of a thing called text pre-processing, which we're not going to go over today. I've done it ahead of time just to save some time, but that is a good call out. All right, so we talked about how the machine learning, right, is taking this big document term matrix and turning it into these word embeddings, which is essentially a smaller space where you have a term with a vector representing that term. So like I said, that's the machine learning. And there are two really primary families of algorithms that do this, right? The first one is a global matrix factorization family. What this does is it just kind of applies to matrix factorization, if anybody's familiar with matrix or linear algebra. And it factors the document term matrix to create a term feature matrix from the text corpus. Before we get too far into this, there's another question. Would weights be categorized under text pre-processing, or is vector representation what the term weight usually applies to? That's a good question. Maybe we can come back to that at the end, because that's going to be a little bit longer of an explanation, if that's okay. So I don't know if maybe we can flag that somehow, or somebody can remind me maybe. But I promise we will get back into that. Okay, perfect. Thank you. So this global matrix factorization family is based on something called the distributional hypothesis of linguistics. This has nothing to do with machine learning, but it's a great example of why data scientists and machine learning researchers need to know their field, or need to know their domain space, because a lot of information from the domain space can help you solve problems, right? So what the distributional hypothesis of linguistics says is that words that are similar in meaning will appear around similar words, right? So if the word, you know, spaceship and the word plane both appear around the words takeoff and land, then they probably mean similar things, right? So this came out in like 1959 by a linguist named Firth, and it's really been fundamental to the whole field of natural language processing. An example of this family of global matrix factorization is latent semantic analysis. And I will say overall that this family of algorithms is pretty tired, right? Like, it's old, it's been around a while, it takes a long time, the results aren't that great. There is a new family of algorithms that are called the local context window algorithms for creating word embeddings. They work a little differently, right? Instead of using matrix algebra, they use machine learning. They use supervised learning because we're trying to predict the meaning of words, right, based off of the words around it. So it's still based off that distributional hypothesis of linguistics. It's going to use neural networks to actually do that process of prediction. An example of this is Word2Vec, which is by far the most popular word embedding algorithm. It's the one I'm going to be using today. And this is kind of like the latest thing, right? So this is newer, this is more effective. At the time I made this, tired and wired was the thing. I don't really think tired and wired is a thing anymore. It's been kicked off the internet, so maybe I'll need to update it. But, oh, here's a question. Are there still use cases for global matrix factorization, or is it totally deprecated? There are definitely still use cases. Local context window is going to take a long time, right? It's going to require a lot of work. It's going to require a lot of data. If you have a pretty limited set of terms, right, and a pretty limited data set, global matrix factorization is going to be really helpful, right? It's going to be fast. It's going to do a decent job. So there are still cases for it. I will say that a lot of the places where there is where text is data, there's a ton of it. So usually Word2Vec is more applicable in a lot of modern situations. All right. So Word2Vec, I mentioned we're going to be using that. There are a couple different versions of Word2Vec. This is as technical as we're going to get during this talk, right? The first one is the continuous bag of words. The continuous bag of words learns embeddings, or those word vectors, by learning to predict what I'm calling the focus word using the words around the focus word. So if we look at this diagram, right, picture 5 words in a row, right, a 5-word sentence. You have this focus word, which is in the middle. It's the 3rd word. What continuous bag of words is going to do is it's going to use the word before that word, then it's going to use the first word, and then it's going to use the word after that word and the last word. It's going to use all of those words together to try to predict what the middle word is, right? So it's going to use the context around the word to try to predict the meaning of the word. This is, we call it a continuous bag of words because the word order, right here, it's not important. It's irrelevant, right? The proximity of the words is irrelevant. So in result, this is going to be pretty fast not compared to the global matrix factorization, but compared to what I'm going to show you next. And it's going to get decent results with pretty common words. The most popular implementation of Word2Vec, though, is what we call the skipgram model. So this is essentially taking that continuous bag of words and it's flipping it on its head. So as an input, instead of using the 4 context words, we're just going to use the center word, right? So we're just going to have a single input, and then we're going to try to project that out and predict all of the words around it. So it's actually a different algorithm, right? That's being, or it's the same algorithm, but it's a different model that's being trained for each one of these pathways, right? So because of that, this is a lot more computationally intensive, right? And more heavily weights the words that are closer to the center word, which is also a good thing, right? So based on the distributional hypothesis of linguistics, if the word is right, if word A is right next to word B, and then you have word G way down that chain, right? Word A and word B are probably going to be more similar than word A and word G. So because it factors in position, the results are typically a little better, but it does take a lot longer because it has to create each one of these models. Does that kind of make sense, the difference between the two there? I think Nate's maybe getting excited a few times here. So that's good. Oh, I got an emoji thumbs up. That's really cool. All right. So we'll go ahead and do a demo then, right? We finally got to code this demo. Can people see my screen with the code now? Cool. All right. So what I'm going to do is I'm going to start off by loading these necessary libraries, right? So I mentioned I'm going to use Spark, and there's an API for Python. It's called PySpark, right? So you can just install it like you would another Python package if you've used Python before. But what I do need to do is I need to establish a Spark session, right? So this is essentially connecting my Python session to a Spark cluster to say when I'm using Spark, use this cluster. So this is where the magic happens, right? So Felicia said you need to do pre-processing on your text. I've already done that. So I'm going to use a text corpus called the Reuters corpus, which is a collection of Reuters news articles, generally like businessy type news articles. There are over 10,000 of them. I think it's like 13,000 some articles in this text corpus. And in total, there are 1.3 million words, right? So that sounds like a lot. This is known as a very small text corpus. It's very efficient to run on. I did some pre-processing on this, right? I removed punctuation. I didn't think about that example earlier. It says I limitize each word. I actually don't think I did. I think I'm going to have to update that. But I'm going to go ahead and I'm going to load in that text corpus, right? And I'll show you a little bit about it. So what this is going to do is it's going to count the number of rows in that data frame or matrix table-like object. So you can see there are 13,328 rows, which are my articles. And then there are, sorry, somebody say something?
No, it's Rafik. He just joined, but I think he's on mute.
Okay.
Okay.
Cool. All right. So if I look at the schema of this, there's one column, just as we see up here. It's called value, and it's an array, right? And it's an array of string elements. So what could that be, right? I'm going to go ahead and show the first 5 rows. So this is what I just loaded in. Each one of these rows is an article, right? And then it separates the words into individual elements. You can see here very early on a consequence of removing punctuation and not doing good pre-processing, right? So my first word is U, my second word is K, right? That should probably be combined to be UK. Same with US, and maybe even something like South and Korea should be combined in this context, right? So there's always a lot of pre-processing you can do to improve things, but it's kind of a balance of time, right? Pre-processing can be very time expensive. So now that I have this text corpus loaded in, I'm going to go ahead and I'm going to define a word2vec object. So word2vec is it's available in a lot of different Python libraries. This is the Spark implementation of it. So this is going to distribute and compute all of this in parallel, right? It's going to be really fast. This actually isn't going to train the model right here. I'm just defining the object. But a few key things here is I have a vector size of 100. So those lengths of those word embeddings are going to have 100 elements. And this window size of 5, remember if we go back here, right, how we have 5 words in this window, and I'm using the center one to try to predict the other ones, right? That's what that window size of 5 means, right? So I'm going to go ahead and I'm going to instantiate that. And then I'm going to call the fit method on it. What the fit method does is it actually trains the model, right? That's a term in machine learning we use a lot. Say, here is this model. I'm going to feed it some data, and I want it to learn or train. I want to train it to learn what I'm trying to get it to learn, right? So that's the process that is happening right now. This is happening in Spark, right? It's distributing all under the hood, and it's going to take a couple minutes. So we're going to jump back real quick and cover a couple more slides before we get to the next section of the demo. So the next section of the demo, right? We've created our word embeddings. Why are word embeddings useful, right? Quite simply, right? I've talked about like previous generations of natural language processing. Word embeddings have completely revolutionized text-based machine learning, right? They have done 2 things really well, right? The first thing they've done is they have collected a lot of information about words that we didn't previously have, right? So word embeddings, remember, they learn from how the word is used because they learn from the words around like a context word. So what that means is that they contain both the semantic and syntactic information of the word, right? If you look at how a word is used in a sentence, you're going to learn things like the meaning of the word, and you're also going to learn things about like when it's grammatically correct and when it's not. And that information is represented numerically, as we've talked about before, which unlocks a lot of different analytical tools and machine learning methodologies that can now be used on those words and language in general. I think that a really good way to hammer home how they catch the semantics again is through this plot, right? So remember, all of our word vectors can be plotted in the same space, right? So, and that they contain semantic information, right? So they're in the same space and they contain semantic information, right? So one would think, right, logic would say that similar words will have similar vectors, right? So what that means is similar words will be closer in proximity, their points will be closer in proximity to one another. And if you look here, that's exactly the case, right? Add and subtract mean different things, but they are used in the same context. They have similar meanings, so they are pretty close to one another. Same with grandfather and grandmother, right? Those are pretty similar vectors. But maybe the words, right, margarita and margarita, despite having the same pronunciation and spelled very similarly, don't mean anything even close to one another, right? They're not used in the same context. So their vectors are going to be far away. And we can go back to our model that we trained. You can see it's finished training here. This cell is complete. And we can show that. So word-to-vec models in Spark are a really nice method called find synonyms. And what it's going to do is it's going to take a word as an input, and then it's going to return the n, in this case 3, words whose vectors are most similar to the vector for this word. So in this case, I'm going to try to find the 3 words that are the vectors that are most similar to the word Spain. So if I run this, you can see I get back Italy, Belgium, and Denmark. This model just learned that from this training process that I ran and that data that I just uploaded. It was able to learn that much that quickly. It's pretty cool. Another example, right? What about the word president, right? President is used in all sorts of different contexts. Let's see how it's used here, right? Chairman, vice, and chief. Pretty similar, right? Maybe, you know, some prefixes, right? Like vice president, some synonyms here with chairman and chief. But you can definitely see that the model in just that short period of time was able to learn more about what the word Spain means and what the word president means. With words containing semantic information, there are also other ways to show that, right? And one of those is an analogy, right? So analogies are comparisons between things to help it better explain them. And analogous relationships, which is a very useful tool here, can be represented algebraically, right? So one might say mother is to grandfather as father is to grandfather, but we could also say mother minus grandfather is equal to father minus grandfather, and win minus lose is equal to rise minus fall, right? So those are analogous relationships we've represented algebraically. And the differences between these words can be represented by their difference vectors, right? So win is to lose, as rise is to fall, and father is to grandfather, as mother as to grandmother. And we'll get into this a little more in a little bit, but it's not a coincidence that these vectors between them are very similar, right? So we're going to go ahead and show that in another demo, if I can remember how to do that. So down here, right, algebraic, I mentioned we can represent these algebraically. And what that means is we can actually set this up to be a solvable equation, right? So we can solve that equation for grandfather to the point where we have father minus mother plus grandmother equals grandfather, and lose minus win plus rise equals fall. This function that I wrote, right, is going to help us solve that equation. It's going to take the first 3 words of that equation as input along with the model we just trained. It's going to find the vectors for each of those 3 words. And then it's going to compute the 4th vector by plugging in that equation that the 4th vector is equal to. Does that make sense? So mother minus father plus grandmother equals grandfather. Instead, to try to find the vector for grandfather, we're going to plug in this father minus mother plus grandmother relationship here, and this find synonyms. So it's going to find the 4 words whose vector is the closest to this part of the equation. Can people see my mouse? Yeah. I lost my little. I lost my little pointer when I went away from slides. So really, what this is trying to do is it's trying to fill in this blank, right? So in this example, we have when. This is actually misrepresented. Oh, it's actually, yeah. So it's the second word minus the first word and so on, right? So in any case, it's still going to fill in that blank. Lose minus win, rise plus rise equals blank, right? So win is to lose as rise is to. Does anybody have a guess of what we're going to see?
Fall.
Fall, right? Maybe. Oh, I didn't define my function. It's not fall, it's decline, right? But who cares? It means the same thing, right? So the closest 3 words to that are decline, fall, and drop. They all mean the same thing. So we know win is to lose as rise is to decline, fall, or drop. It's a very cool thing, very easy, right? This is all the code that we've run. And it can come up with really powerful things, and it can learn really powerful relationships as demonstrated here.
Mark, there's a couple of questions for you.
Yeah, question. So the first question, how unsupervised can pre-processing get? How much can be automated? That's a good question, right? So pre-processing, again, what we're doing to our text and our language before we even put it in an algorithm. There are a lot of libraries out there that can automate that, right? So there's a library I used earlier in this demo called NLTK. That is the Natural Language Toolkit library in Python. And there's a lot of stuff in there that can help pre-process that really easily. So I say I removed punctuation using the NLTK library. I can tell you I did not go in and type in every punctuation symbol, right? Like it does a lot of that for you. So it can be pretty automated. What I will say is that there are cases where you might want to keep some of that stuff, right? Like you don't want to just blanketly pre-process and water down your data until necessarily you might know you have to, right? So I brought up the example of lemmatizing words, right? Or stemming words, right? If I'm going to stem a word, right, I'm going to take away a lot of its meaning. I'm going to take away its tense, and I might be losing a lot of information there. So while yes, a lot of it can be automated, it's not necessarily always best to just go ahead and blindly apply automated pre-processing techniques to it before you even try to model it. The next question, where is this data being processed? So that's a good question. Spark, as I mentioned, is a clustered computing framework. One of the nice things about Spark is it has a few different nodes, or a few different modes. So it can run in a cluster, right? Where my machine could be a driver node, and I could be putting it out onto a cluster, whether that's in the room or in the cloud. This, however, is running in local mode. So I have a 2018 MacBook, right? So what's happening is I have a single core that's operating as the driver, and it's distributing it onto the rest of the cores on my machine. So it's distributing that way. So, I simplified it by just talking about computers. There's another layer to that is cores, either within a computer or within a cluster. So that's how it's being processed. Hopefully that answers your question, Philip. Yep, cool. All right, so I think we had just shown this analogous relationship, right? When it's to lose, as rise is to decline, fall, or drop. Let's head back here. And let's talk about some other things that word embeddings can do. So I mentioned semantic relationship and showed that a couple different ways, or semantic information. It also contains syntactic information, right? So we can learn things about grammar, right? We can do this using analogies as well, right? So add is to added, as subtract is to subtracted, right? And cat is to cat, as dog is to dogs. You can see that represented visually here. And again, and I'm going to hammer this a little more this time, these vectors end up representing ideas. And that's essentially what we're finding here, right? Is that this vector between cat and cats and the vector between dog and dogs is going to end up representing the plurality vector, right? So in this space, if we draw that vector from any singular noun, we should hopefully get its plural noun end result. So if we had monkey here, right, we could draw the same vector, right, this way, and get monkeys in result. The same thing here, right? This is a present to past tense vector, right? So the difference here goes from present to past tense. If we had, divide, right, we would have divide to divided if we drew that same vector. So again, let's go ahead and view this as an example. I will say that syntactic relationships are a little bit harder to learn. And because I'd kind of, lemmatized and stemmed some of my data, it might not work. Instead, and another reason for doing this is to show you that you can do it this way as well. I'm going to load in a pre-trained set of embeddings, right? So I'm going to go ahead and get it started because it's very big and we're not operating in Spark. So now I'm just operating on that single core. And it's going to load in a set of word embeddings that were developed and trained by Google, right? So this is done using news documents again. That's an important parallel, right? There are over 3 billion words, including in the training corpus, compared to our 1.3 million words from the Reuters example. So this data is a lot bigger. and then it ends up having 3 million words with vectors. The reason that that's a little bit smaller is because they probably removed some words like Felicia mentioned, right? We call them stop words, the, that, and. But also, sometimes words just don't appear frequently enough in the text corpus for us to have be able to calculate a meaningful representation. So a lot of the time, there's a minimum threshold in these algorithms to determine whether or not they're included in that embedding set. So I'm going to keep talking while this is loading. It should be done by the time I'm done. So we use this analogy framework, right, to show how the meaning of words, right, the relationship between them. We can, as I mentioned before, we can do that with tense as well, right? So add minus added is equal to subtract minus subtracted. But this one's a little more interesting, right? We're not just adding ed to the end, right? Run is to ran as shrink is to what? Does anybody have a guess on what we're going to use, how that blank is going to be filled in? Shrunk. We have 2 votes for shrunk. What did you say, Joe?
I said shrank, but I like shrunk better.
Shrank or shrunk? We'll see which one it's going to be. Right now, I'm computing add is to added as subtract is to subtracted. First result. Very cool, right? We just loaded in this pre-trained model. Very easy. Now we can find the relationships, or we can view present to past tense. Run is to ran as shrink is to, I think we have 2 shrinks and 2 shrunks. What's it going to be? Shrink wins, right? So shrink is the first result. Shrunk is the second. It's very close, but it identified both of them, right? And just like we saw with win is to lose, as rise is to decline, fall, or drop, they can both be right. And that's one of the really cool things about these. So that's tense, right? Verb tense. Plurality is another example, right? So we're going to use that same get analogy function. I didn't mention this up here. I got distracted, but I had to write a different one because we're now using a different package, and its embeddings are in a different format. So the first one was for Spark. The second one is for Google embeddings. Oh, I got shrank. The problem might appear for verb hang. We could try that. Let's run hang real quick. So run is to ran as hang is to hung, hanging, hung, not hanged. So yeah, it's fun. It's when I wrote this, I like played around with these for hours just because it was so much fun to see what it would come up with. So plurality here, right? So similarly, right, we talked about cat and cats. Cat is to cats as dog is to dogs, right? Other options, pets, canines, pretty cool. Duck is to ducks as goose is to geese. It has Canada geese and mallards here as well. And then let's look at dogs, dog to dogs as ox is to oxen, oxes, yaks. I don't know what a yak is, but something cool here is that donkeys is here. Donkeys are pretty similar to these things, like to an ox, I guess. How does it do for moose? Good question. Let's put in moose. Ooh, elk, caribou, and deer. So not as good. But something you got to remember here is that we're training these on news documents from Google News. You know, I don't know how often the plural word for moose, right, is going to appear in something like this. So we'll talk about that a little later. Need to use the Canadian corpus. Yeah, that's true. we could do that. All right. So the last one, right? So Felicia, it's your time to shine. So dog is to dogs as tableau is to what? Let's check it out. Oh, it's tableau. How interesting. So I found this because I was just trying to think of like the most uncommon words that I know that would appear in English, right? That it's not something that I think about all the time. And as I was doing this, right, I was looking at stuff about the Southwest Florida Tableau meetup, and this was on my mind, and I said, what's going to come up? This came up, and I was very excited about it. All right, so we're going to keep moving along here because I know it is 8 o'clock. So next, we're going to talk about how to use word embeddings, right? So I think people had some fun there, but obviously drawing lines on graphs and learning the plural for tableau is not super useful, contrary to what some people on the call might think. Word embeddings are powerful in how they can be used to solve problems at scale, right? There needs to be a practical power here. Truly the time to draw the line. Yeah, that's funny. So think back to the example machine learning problems we thought of, right? We had predicting book sales based on the author's previous sales, book price, release date, classifying customers into actionable groups based on their spend behavior, visit frequency, and common modality, and then identifying what calls are fraudulent based on who's making the call, the length of the call, or whether or not somebody answered. Has anything we've done today improved our ability to solve any of those problems? Remember, we talked about all of the data here being numeric, and that's still true, right? Like this drawing lines to find out that dog is to dogs as ox is to oxen hasn't solved this problem. But remember that word embeddings are vectors, right? And the majority of machine learning algorithms, right, take vectors as input. Remember when we went back to that supervised learning, right? And we had those little black, when we went back to our supervised learning algorithm and we had those little black tables representing different, what I called features, right, going into that learning algorithm, right? That is essentially what a word embedding is, right? It is features, right? It can be that input data to those supervised learning problems. So now that we have this text information, we can expand our data set to be far more rich, right? So on our first problem, we can now add the actual words of the book, right? The story, the topics, all of this information is now available numerically, and we can use that information to predict whether or not people will like it, right? I'm sure some of you have seen somebody post on Twitter or something, I wrote an AI bot to write an episode of The Office, right? Like that is the power that we're now working with, right? We can use the actual content to predict whether or not this is going to sell. At one of our meetups, I think it was a code collab, maybe our last one, we went out for drinks afterward and we talked about how we can use AI to write songs, right? Whether that's music or lyrics to be really popular, right? And I knew that our next meetup, I was going to give this talk and talk about this exact thing. So I didn't want to spoil it then, but effectively that's exactly what this can be, right? Is that you can write words to a song, feed them into an algorithm that's going to predict whether or not that song's going to be successful commercially. The other example, right? We talked about classifying customers into groups based off different things. We can now include those reviews and comments I alluded to earlier, right? We know this customer is very annoyed about having to chase down shopping carts all the time, right? Like we know that this customer really hates it when they pull up to pick up their groceries at curbside pickup and those groceries aren't available right then, right? We can now capture all of that in an automated fashion, right? And then classify customers and act upon them based off that information. And then finally, what calls may be fraudulent, right? We can now use the actual words that were said on the call, right? To help us learn whether or not those calls are fraudulent. I can, right? You pick it up, you can tell within 3 words, right? Now the algorithm can as well. So this opens up a world of possibilities that can be solved using machine learning. I know when I think about this stuff, especially as I was learning this, having been a data scientist and worked in this field for a little bit, I got chills because all of a sudden I could tell all of my product owners that, hey, we can do this and we can do it really well. So it's really exciting stuff. And word embeddings are the fundamental building blocks of all of it. But they are not perfect, right? There are some things to be aware of. 2 key limitations I'm going to call out here. The first limitation is that, as I mentioned earlier, there can only be 1 vector for each word. But the problem here is that sometimes words have multiple meanings, right? So we're going to talk about here, we're going to do a demo, right? The word good, right? So who thinks that they can identify some synonyms for the word good? Hopefully people. Great, fantastic, marvelous. Yeah, maybe marvelous will come up. Product, Nate. Spot on. When we use the Reuters model to find the synonyms for the word good, we get back electronic, manufactured, electrical, in the similar context to what Nate said, product, right? So that is because the word good can only have one meaning because it only has one vector. And in that vector, and that vector is trained based off of how the word good is used in Reuters text articles, Reuters articles, right? And Reuters talks about business things, right? It talks about the economy. And so electronic goods, manufactured goods, and electrical goods are what it comes back with. In a similar vein, the word right. We could see wrong, right? We could see left. We see entitle, entitled, and entitling. And stuff about the economy, those words can come up in the same context as right pretty frequently. So that's one limitation of these, right? Another limitation, or not another limitation, not yet, but let's look at what these words might mean if we trained a model using a different text corpus. So another really common text corpus for learning natural language processing is the Gutenberg corpus. The Gutenberg corpus is formed from a collection of novels, right? So this is going to be fictional writing. This is not a huge text corpus, but you can see I train it here. This is all commented out with a vector size of 300, a window size of 10. I'm iterating a few times. So I'm changing some parameters here. And what that means is this takes a longer time to train, even though that it's in Spark. So I've gone ahead and done it, saved it, whoops, and I just loaded it back in. That's one of the really cool things about these models, right? You train them, you save them, they're done, and you can just load them when you need them after that. So I've loaded it back in as this Gutenberg model. I'm going to find the synonyms to Gutenberg model, or to good using the Gutenberg model, and I get natured, much, and well, right? Very different meanings for the same word than we had up in the Reuters model example. The word right, we get left, admirably, and decide. Decide's a little fuzzier to me. I can kind of see it, but left and admirably, I can see how those words are used in similar contexts to the word right. So let's talk about our other limitation now, right? So the other limitation is that most embedding algorithms require a really large amount of data to successfully learn those embeddings. So I've shown you some really cool examples of these things doing really cool things, right? We tried Moose, it didn't work. It got close. Sometimes it doesn't get close, right? So this Gutenberg model, those novels, it might seem like a lot of text, but it's really not a ton of text. It's a pretty small model. So if we try to solve this analogy problem, right? Father is to mother as grandfather is to, we would expect a grandmother. But if we run this using the Gutenberg model, which has much more limited data, we get back Jerry, muskrat, and anyway. Definitely not good, right? I don't know if anybody has read any books that can tell me why the Gutenberg corpus thinks that father is to mother as grandfather is to Jerry or muskrat, but if you can, I'd be very interested to know. All right, so I'm catching up on some comments here. So Waleed asks, are there any non-linear examples, or is that beyond NLP? Unfortunately, I missed the context of what you were talking about there. So if you could follow up on that, I could answer. Joe says, with a news article corpus, so interesting. What's the context to that? Did you say something?
Joe, you're mute.
I missed it.
Can you hear me now?
Yes, I can.
It was just the synonyms of right were so not what I was expecting, but in a news article context, talking about law and the economy, it made sense.
Yeah, for sure. Yeah, no, it does. It definitely shocked me when I saw that as well. And then Crystal says, I feel like this is something that Grammarly uses as well. Certainly, Grammarly is like a natural language processing powerhouse. They're really good. To be able to, like you said, style of writing for sure. You can say like these words have this different style. I think one of the most fascinating things to me is, how they're able to use the syntactical information picked up from this stuff to be able to fix your grammar, right? Like they use this, not all like autocorrect things use that. A lot of them are like pre-programmed, hard-coded rules, but be able to use this to like know that, hey, this word should be subtracted instead of subtract, I think is really cool. And then Matthew sent out what looks like to be the Gutenberg corpus. We can pull that up real quick. So this is, the Adventures of Jerry Muskrat, right? There it is. There's the answer. I've solved the problem. I don't know that I'm going to read the book, but thank you, Matthew. That was very helpful. I will look into more information around it. So let's move on to the next example, right? So under the Google embeddings, right, where we have more data, father is to mother as grandfather is to grandmother, aunt, mother, granddaughter, right? They all make sense. They're not all right, but they all make sense. So you can see how having this much more data can be really influential to one of these models. All right, so we're going to go ahead and we're going to round this out by talking about how this transitions into really modern machine learning, right? So I mentioned that this has been like the fundamental building block of modern machine learning. And there are two core algorithms that, these are just my opinion, I think that are based on this idea that are really helpful in the real world. The first one is doc2vec. Doc2vec is very similar to word2vec, except for it creates a vector for an entire document of text instead of just a single word, right? So a lot of the time when we are trying to use this in a real world, right, we have words with text information, or we have words, right? But we don't want to know what the word means. We want to know what the whole collection of words means. And a document vector can tell us that, right? So I've talked about customer comments a few times. I've actually lied to you, right? Word2vec is not the most useful for customer comments because customer comments are all differing in length. And that poses a problem for a lot of machine learning algorithms that expect the same structure of input data all the time, right? So what doc2vec does is it says, hey, take this whole comment, all of the word embeddings in the word embeddings for all of the words in the comment, and condense it into a single fixed length vector, no matter how long that comment is. So it's much more actionable and extremely useful. I used it a lot when I was a data scientist and got really good results with it. The next algorithm is seek to seek, right? So a sequence of words to another sequence of words. And there's a star by this one because this one is the holy grail of modern natural language processing. It accepts that sequence as input. It uses a neural network to encode those into vectors, the sequence of words into vectors. And then it's going to do, some math, do some neural network stuff, and then it's going to decode that back out into a different sequence of words. And you can train this to happen to do a lot of different things. Seek to seek was originally built for machine translation, right? Does anybody notice that Google Translate has gotten a lot better over the years, right? Seek to seek is why, right? So they can take in a sentence in English, do a bunch of massaging, encode it, do more massaging, decode it, and then they can end up with that same sentence in a different language. Summarization, right? So I have this document. It is 1,000 words, but I want to represent that document in 100 words. Seek to seek works for that as well. You just change the size of the input and output sequences. Conversational modeling. This is how chatbots work, right? Seek to seek, the same thing. And image captioning, right? So I included this one just for a little curveball at the end, is that all of these being represented as numbers, right, allows us to use numerical computing on them, right? But we can combine that with things that actually are numbers, right? So we can take in an image that is represented as an embedding, right, in that same vector space, or in a vector space, and then we can apply a seek-to-seek model, but the output we want might be words, which how cool is that? And then it comes up with a caption of what's happening in the image. So this is how all of this stuff works, right? You can see how the word embedding is the fundamental unit, and then you combine these word embeddings in really complex ways with other data, and you can end up completing all of these really, what were once thought to be impossible tasks. So I've realized we covered a lot today. What to do next, right? So no matter where you are, no matter how much you followed, here are some resources for you. Zarella said I shared some of these in the Slack machine learning Slack channel. I certainly have. I don't think I've shared all of them, but these are some of my favorites, right? If you're new to machine learning, you thought what you saw today was really interesting, I highly, highly recommend this book, Introduction to Statistical Learning. It gives the background of a lot of machine learning concepts, as well as introduces you to some key introductory algorithms. It's developed by the Stanford Statistics Department. It's available for free online. If you would like to, it is written in R. It uses R. If you would like to use Python instead, there's a Python book that is pretty similar. I think there are also the exercises are written in Python are available online to this first book as well. Intermediate, a few of my former colleagues at both Kroger and at University of Cincinnati, Bradley Bemke and Brandon Greenwell, have written a book called Hands-on Machine Learning with R. It was the top R textbook, top selling R textbook in 2019. They're both really good. Brandon specializes in interpretable machine learning, which is a whole separate field about trying to understand why these machine learning algorithms are making the decisions they are. A really, really popular book. In fact, I think Joe is working through it right now. Hands-on Machine Learning with Scikit-learn and TensorFlow. That's a Python-based book. Scikit-learn is by far the most popular machine learning library in Python. And then TensorFlow is a deep learning library that has APIs in Python as well. And then if you're interested in learning more about deep learning, which is really how a lot of this works, I recommend this book, Deep Learning with Python by Francois Cholet. He works at Google. He wrote a library called Keras, which is a good API into TensorFlow that's a little bit more friendly to use and very approachable. And this book is written for people who have no exposure to machine learning, which is awesome. So you can just jump in right there if you want. It's not very math heavy, it's very applied. If you're interested in natural language processing, maybe you already know a little bit more about machine learning. As far as introductory content, I strongly recommend this Text Mining with R book. It's available for free online. It's written by two authors, Julia Silge and David Robinson. Julia Silge is the chief data scientist at Stack Overflow. David Robinson formerly was the chief data scientist at DataCamp. So they're really smart people, really good writers. And it covers a lot of the basics of the natural language processing workflow, things like pre-processing that we already talked about. Word embeddings, if you're interested in learning about them, there are some pretty approachable papers written about them. Thomas Mikolov is the guy who created Word2Vec. He works at Facebook, and he has these two papers about Doc2Vec and Word2Vec that are very approachable and very interesting. We talk a lot about that distributional hypothesis that I mentioned. I recommend reading that too if you're just a curious person and you like to learn things. I already told you I lied to you once. I've actually lied to you twice. I told you that Word2Vec and local context window methods were wired. They are in an applied setting, but there is a new way to create word embeddings that are called global vectors, commonly referred to as GLOVE, that are becoming more popular. It just came out like a year ago, but it's not implemented in Spark, so it takes a really long time to run. So there's that as well. And then the thing that I'm most excited about on this that I'm doing next is I'm going to, there's a class out there that does cost money, but all of the material is online for free, called Natural Language Processing with Deep Learning through Stanford. And it is like the cream of the crop natural language processing course. So if you're interested in learning more stuff, I recommend reading maybe up on some text mining stuff or natural language processing basics, and then jump into this because it is a little bit more advanced, but it is very, very well regarded. So with that, that is all the content I have. I'm going to follow up with some questions real quick here. Can models with vectors be used as models, increasing the vectors? I know, not really clear, but in my head sounds good. So I guess this is a good thing to talk about, right? So like I've called things models a few times, right? So word-to-vec models are trained on a text corpus. And then we have this model, and the model is really just the machine learning part that gets from the big text corpus, that document term matrix, to the word embeddings, right? It's just the algorithm, right? Or the trained algorithm. On the other hand, we have the vectors, right? And the vectors aren't actually a part of the model. Frequently, in a lot of these libraries, they are stored as part of the model object, but they're really the output of the model. So that hopefully addresses that. What about upcoming neural network from scratch by Syndex? I actually don't know what that is. Waleed, I don't know if you want to kind of elaborate on that a little bit. Maybe that's what this is, this link. Jerry Muskrat's going away. Neural networks from scratch. Yeah, this is probably a really good book too. I'm not as familiar with it, but it looks, all of the stuff on here looks really good. I like the visualizations. All of the concepts definitely are like pretty popular. So I don't know anything about this book. I'll look into it more. And then Nate said, can you share the Jupyter notebook for those interested? Absolutely. I will share it in the Slack channel. I will say, I'll also send you a link on maybe trying to install Spark, because you are going to have Spark installed to run that notebook. But at a minimum, I'll run all the cells, right? Save it so you have the output and send it over so you can refer back to it. Yeah. Any other questions? I know I took a little longer. I was having fun. No? Cool. Well, thank you. Oh.
I think it's just, there's a couple more.
Share the references listed in the last couple slides to Slack. Absolutely, I will. I will do that. Not these references, but the these ones. I absolutely will share those.
Can we have your entire presentation?
Yeah, I'll send it all.
Awesome.
Yeah.
Thank you.
Cool. Yep, not a problem. And then do people?
I had a question.
Yeah.
So you were working locally on this. What helps you determine when you need to move into the cloud and get a whole bunch more resources? Is it the size of the corpus? And if so, like, what are the thresholds that you look for, okay, I need to get away from local here for this project?
That's a good question. The size of the corpus is definitely going to be part of that, because if the corpus itself can't fit into the memory, even if it's distributed, right, it's not going to work. I will also say it's the complexity of the algorithm. So I don't know if you remember here, I loaded an algorithm. I think I went by it. I loaded an algorithm that I had already run, right? This Gutenberg course is not very big, but I made this algorithm a little bit more complex, this model a little bit more complex, by increasing the vector size, right? That just requires more data. A lot of the iterations are going to have to work with more data. It's going to take a longer time. The window size, the same thing. So I would say those are the two primary factors: is the complexity of the model and the size of the text corpus. In terms of when you need to move into the cloud, I mean, that's up to you, right? Like, how much time do you have? How much patience do you have? I think that answers like that question the best I can. I wish I could give you more, but I think it's just kind of like a personal thing, and your like constraints, both time and cost. I mean, obviously, if you move into the cloud and you get more resources, things are going to move a little bit more quickly. But it's just, I think it's more of a constraint problem than anything else. And I think there was another question there.
Yeah, no, you answered it. Basically, it was like,
okay.
What determines when this is too much for local. And I didn't know if like maybe there were ratios of like corpus size to system RAM or something like that. But I guess if the models themselves and their configurations can heavily change the resource requirements, then it's going to depend on each project.
Right, and there might be guidelines on that. That's something that I'm not familiar with. working at Databricks, I'm blessed with every single notebook I log into is not actually through Jupyter, it's through Databricks in our own platform. And we have auto scaling compute power on that platform. So that's not something that I come across very frequently, but it might be out there. There's another question in here about, do people build their own corpuses? Seems there would be a few giant ones that get reused. Absolutely. In fact, for like truly doing this professionally, a lot of people just use pre-trained word embeddings, right? Like, why go through all of this work if that Google embeddings work so well? And that's not even one of the biggest ones. So there are pre-trained embedding sets out there. Where you might want to train your own embeddings or create your own model is when you are creating your own corpus, right? So the reason you would want to do that is because you are interested in what words mean in a very specific scenario, right? So I used to work on a recipes team at Kroger, and we were training a Doc2Vec model to get better data around recipes and both ingredients and instructions in our model or in our recipe data set. And there are a lot of words that mean different things, right? In different contexts, as we saw. We wanted to know what words meant in the context of recipes, right? So in that case, we used our own recipe data and trained a Doc2Vec model on that. So that's when you would want to create your own corpus with that information and train your own model, is when you're very interested in what words mean in that specific context. I can tell you one of my favorite corpuses that I've used is the collection of text messages between me and my girlfriend. It's very fun to look at. It's a lot of different interesting problems you can solve with that. So that's a fun example if anybody's interested in that. And then somebody else says, how do you process sarcasm? So that is one of the major advantages of that seek-to-seek model, right? So in Word2Vec, every word only has one meaning, right? If a word is used sarcastically mostly, it's going to capture the sarcastic definition of that model or of that word, and vice versa. But when you use seek-to-seek, remember, it's looking at all of the words as an input around a word, and then it's returning a collection of words as output. And because it's looking at all of them coming in, then it can tell from the context of those words, hey, this word's being used sarcastically this time, right? And then it can respond accordingly. So it's really cool. I'm not sure if anybody here has, I forget the name of it. It's called, Google released it. It's like their bot that orders things for you and like gets you reservations. Does anybody remember the name of that? No. Hold on. Google ordering bot. Google Duplex is the name of it. So Google Duplex is this like super smart chatbot that Google created about a year ago. And yeah, it was May 2019. And it can do like unbelievable things. I recommend checking it out to see this at like its full power. But it's good. The reason I bring that up is that it processes sarcasm very well. So cool. It looks like that's all the questions in the chat. I know we are about out of time. Filled it up with QA, so that's good. Thank you everybody for calling in and listening to me talk about things that I like to talk about. It's always fun. With that, I guess I'll pass it back to you, Zarella.
Okay, thank you very much.
This is great.
Thanks, Mark.
Did someone have another question over there? No?
Just thank you, Mark.
Yeah, no problem.
Yeah, this was amazing. You're a very good explainer.
Thanks, yeah.
So just a couple more minutes. We have a raffle. Derek, are you there?
I'm here.
Okay. Derek was going to write a cool script to see who was going to get the, what is it? I forgot.
The JetBrains license.
JetBrains. Yes. So go ahead. I give it to you.
Okay, hold on a second. Let me check it real quick. Hold on, sorry. I was just thinking about like last minute thing.
I'll put all of us back.
Yes, good. All right, just making sure I got everyone in there. I think I've got everyone in there. Okay, it's no big deal. But since we can't do tickets like we normally do, I just have this right here. So here we go. No, it's not what I want. Okay, here we go. Here we go. Okay.
That's fun. That's awesome.
Crystal.
Crystal.
Hey,
Crystal.
That's fun.
funny.
That's pretty cool.
All right,
Okay.
Crystal. All right, are you available? Are you there? I got messages.
Yeah, she's there. Crystal, you're on Slack, right?
Okay. Yeah, just message me. I'll find you on Slack. Is it okay if I send you your license thing on Slack? I'm looking at the chat right now. Okay, cool. I'll send it to you there. All right, and I actually think we have another one because we didn't have a meetup last month, so we'll run it again.
This is fun.
All right, Mark.
Mark,
Hey,
Oh.
Mark, hooray.
Oh,
awesome.
Awesome.
thanks. Thank you.
Yeah, absolutely. So you both are going home with a 1-year license to any that JetBrains offers. So I'll send those to you on Slack.
Great. Love
There-
JetBrains.
They're worth like $70 or something like that, right?
Yeah.
Yeah. Awesome. Thank you guys.
Thanks.
I'm gonna take usually I take pictures, but I guess I can take a screenshot of this. But thank you everyone for coming. Mark, that was very nice. You did an awesome job.
Great job, Mark.
Yeah,
Yeah,
that
great.
was very cool. And remember, he's on Slack. If anyone
Thank you.
here is not on Slack that would like to be. No, everyone is on Slack. Okay, awesome. If you are not, just reach out to me or Derek through the meetup message, and we'll send you an invite. But already, guys, well, this was fun. I miss seeing everybody in person, but hopefully one day soon. So we don't have any happy hour after this. That's normally what we do, but it's okay. We'll find a happy hour time for all of us. Oh, look at you guys. Thanks.
Thank you, everybody.
Thanks.
Thanks,
Thanks.
Bella.
Bye,
Take care.
guys.
Thanks, guys.
Good
Miss you
night,
guys.
everyone.
Bye.
Thank you.
Yeah.
Bye.
Cheers.
I'll wait until everybody leaves. I'm gonna kick out.
Well, it's not letting me leave the meeting.
No. Wait. Why?
I don't know.
No. Bye.
I'm not still sharing, am I? No.
No. That's weird. Maybe I'll just end the session. Okay. I guess I'll just end it. It's okay.
All right.
Oh, I have to stop recording too.